Okay, so we're going to start looking at the review number 5. Let's get it. And we can go back and catch 1, 2, 3, or 4 as needed. So number 5, we have this ice cream shop where customers may choose to sprinkle toppings on their ice cream. Toppings are classified as either candy or fruit. Consider the choice experiment where the choice of toppings, candy or fruit, C or F, is recorded for each of the next 2 customers who order ice cream. List all the units in the sample space. Now, I will say this one's a little misleading. We're going to assume that the customer, if they pick a candy topping, they're going to pick another candy topping. So really, I should take 2 out and say they pick 1 topping, just to make it clearer. Each customer is going to pick essentially 1 topping. So we want to record all the different ways that 2 customers could pick a topping. I want to say they can choose 1 sprinkle topping, just to make it clearer. So what are our ways that we can pick a topping for 2 customers? Well, they could both do the candy, or what could they do? They could both do fruit, or so just like flipping a coin, essentially. Both get heads, both get tails, 1 heads, 1 tails, 3 tails, and then heads. So same concept here. Okay, B is asking us to use our sample space in part A. List the outcomes for each of the following events. So A says the event that both customers pick candy. So which event up here uses both customers pick candy? C, right? So that's what we put here. B is the event that both customers pick the same type of topping. C, F. And then C, the event that at least 1 customer picks candy. That's right. Okay, so that's those 3 on part B. And then part C asks us to make a tree diagram. So I'm going to start at the beginning. If I split off, what are my 2 options? C and F. If I split off from the C, what 2 options do I have? C or F. Which that one becomes CC, that one ultimately would be, we'd read that as CC. That's CF. You don't have to do this last part here. This is just reading what the outcomes are. Okay, if I split off from F, what are my options? C and F. So again, that would be FC. This one would be the outcome FF. So, does number 5 make sense now, Will? Good. Okay, is there any other y'all want us to jump to? 6, okay? We'll go to 6. So, they give us all this nice information about some Australian diamond python. Now they give us 2 habitats in buildings, which would not be a good habitat. I do not want a snake in the same building I'm in.
Right.
And then other. And then the seasons, spring, summer, autumn, and winter. So just for reference, for spring, I'm going to use SPR. For summer, SUM. A for autumn, W for winter. Building, I'm just going to use B. Other is going to be O. Okay, so A asks us to find the probability a randomly selected diamondback would be located in a building. I'm just going to go and start right. Probability of building given that it's spring. So remember, this is the probability of their intersection divided by the probability of which one? Spring. Now, I know these aren't probabilities, but the concept actually is still the same. So what is the intersection building in spring? 10 goes on top. And then spring total, 353. So this would give us our probability. So then, to 4 decimal places, what is that approximately?
0.02.
What's that?
0.0286.
0.0283. Okay, so that's part A. B's asking the probability that a randomly selected diamondback would be located other than in a building, given that it's spring or summer. So setting it up the same way, the probability of other intersect spring or summer. Over the probability of spring or summer. Okay, so we want other in the spring or the summer for the top. So what would our intersections be? 343 and 273. That's what we'll have on top. 343 plus 273. Over, now we just want the totals for spring and summer. 353 plus 309. So if I add these up, 6, what is it, 616? 12, 6. And to 4 decimal places, that's approximately what? 0.9305. Okay, and then we have the last part. A randomly selected diamondback is found the probability a randomly selected diamondback is observed in a building, the probability of building, or in the summer. That's going to be the probability of building plus the probability of summer minus the probability of building and summer. So here we actually need probabilities. So probability of the building would be 63 over 997. Probability of summer would be what? 309 over 997. Minus probability of building and summer. Building and summer. So 36 over 997. If I do the math here, what should I get on top? Let's see. 336 over 997, which is approximately, no, exactly 1/3. .337. Okay, questions on number 6?
Mr. Schultz, what are our notes for doing all this kind of stuff? It's like, I can't find them.
So, is that assignment 3.3?
Like, I'm getting my notes.
Section 2.
6.6.
6.6.
Oh, okay, that's it. Thank you. Appreciate it.
Okay, what next one would y'all like to look at? Yes.
What would go for B?
For B,
Yeah, I never wrote that down.
there you go.
That's 7.
7? Okay. Oh yeah, 7, part D is a little tricky on 7. I say that, but I'm kind of biased because it's only tricky because it tricked me up when I was creating the key. Okay, so I'm not gonna read that big paragraph. They give us some information about people who registered to vote and then who they voted for. So, in case y'all weren't able to figure it out, this is the party that each person ran under. It's not saying use D for Napolitano or for Salmon, I guess that's how you'd say that name. That's how it's spelled at least. And I for Mahoney. That's saying Napolitano ran under the Democrat. Salmon ran under the Republicans. So I'm actually going to use N, S, and M for these. I'm going to keep the D, R, and I for how the voters register. Okay, part A asks the probability that a randomly chosen voter voted for Napolitano. The probability of N. Well, how many voted for Napolitano? 282. And then how many total voted? 600. So this would equal 0.47. Yep. Part B asks the probability that a randomly chosen voter is a registered Democrat. So probability of Democrat. Well, how many registered as Democrats? 216 out of the 600 total. So what should that give you? 0.36. Okay, questions on A or B? Okay, then let's go to, I'm going to have to go to the next slide to get to C. What's the probability that a randomly chosen voter cast a vote for Napolitano, the probability of Napolitano, given that they were Democrat? So this is the probability of Napolitano and Democrat over the probability of what? Democrat. The second one's always your denominator. So Napolitano and Democrat, I think that's 184. I made this table way too small for me to see this far away. And then the probability of Democrat, or the number of Democrats, is 216. So this is approximately equal to what? What's that? 0.8519. Okay. Okay, so commenting on this election, a local reporter said Napolitano won because she attracted a larger share of crossover voters. And then, in case you didn't know what a crossover voter was, the definitions included. So a crossover voter is defined as one who votes differently than his or her party. So it'd be like a Democrat voting Republican or Independent, for instance. What's the probability a voter casts a vote for Napolitano given that they were a crossover? Okay, so this is the probability that they're Napolitano and a crossover. the probability of being a crossover. So let's go up to our table and actually circle all our crossovers. So for the Democrats, if they voted Republican or Independent, they're a crossover. Republican would be if they voted Democrat or Independent. And an Independent would be those that voted Democrat and Republican. So essentially, everything but the diagonal. So we want Napolitano and crossover. So that's the two on top we circled. 42 plus 56. Then we need all our crossovers. So I know 42 and 56 are crossovers. Plus 26 plus 45 plus 6 plus 5. So let's see, on top I'll have 98. On the bottom, let's see, what is that? That's 50. What, is it one, you said 170? That's probably it. I'm trying to, that's what I'm trying to do. Now I have 98. I got 50.
That's 180.
180, okay. Which is approximately what? 0.54.
Okay, 4 repeats.
You said it,
It would be like 5 4.
oh, 54 repeating. Okay. So yeah, she got a little over half of the crossovers. Okay, so that was 7. D was the tricky part on that one. Yes. Okay. What's the next one y'all want to look at? Eight? Sure. Okay, as every Girl Scout knows, statistics teachers seriously love Girl Scout cookies. In case you're wondering, the peanut butter patties and the caramel delights frozen, pretty good. And the Thin Mints frozen. Just freeze them all. I'll eat them frozen. Don't need to wait to thaw them. The number of boxes of Girl Scout cookies statistics teachers order, like all important decisions made by statistics teachers, is determined by independent rules of a 4-sided fair die. If a 1 appears, we order 6 boxes. If any other number appears, then we order 2 boxes. So A asks the probability a statistics teacher places an order for 2 boxes. The probability of 2 boxes. Well, how many ways can I get 2 boxes? If I roll a 1, I get 6 boxes. Any other number, I get 2 boxes. since it's a four-sided die, my other numbers are 2, 3, and 4. So what's the probability I only get to order 2 boxes? 0.75. That's right. Or you could have also said 3/4. But yeah. Yeah, it's four-sided pair die. Okay, B asks what's the probability that 2 independently chosen teachers each order 6 boxes? The probability.
1/4 times 1/4.
Yep. Probability of 2 teachers each ordering 6. One-fourth times 1/4. They're independently chosen. So 1/4 times 1/4 is 1/16. I want to see when that was a fraction for this one. Questions on those two? Okay, next one. What's the probability that 2 independently chosen statistics teachers, the first will order 6, and the second will only order 2? The probability that first orders 6 and second orders 2. So what's the probability that the first will order 6? 1/4. What about the probability that the second orders 2? Okay. 1/4 times 3/4? 3/16. Okay. Now we have part D. What's the probability that for 2 independently chosen teachers, exactly 1 will order 6 boxes? Only 1 can order 6 boxes. Well, let's see. We have, what are the 2 ways that can happen? The first gets 6, and second gets 2. Or we could have it switched. First gets 2, and second gets 6. So let's call these events A and B. What's the probability that A occurs? Well, we just calculated that one actually up above. 3/16. What's the probability B occurs? 3/16. Now, can you have it to where they have something in common, like A and B share something in common? Are they mutually exclusive? What's that? So, what's that?
They're over the same thing, so they work.
Well, these two situations would be, because you can't have, yeah, you can't have, there's nothing overlapping. Either the first one's getting 6 or he's getting 2. And the same thing with the second. She's either getting, or he's either getting 2 or he's getting 6. So, to get the probability of A, exactly 1 for order 6, we simply add the probabilities. That would be 6/16, which reduces to 3. Do y'all want to look at 9 or 10? 10? Yeah. Okay, so for 10, the one I actually, just to make sure I hit before we run out of time, is part C, the probability of having a cat and a dog. We have to use the information they give us. So this is the same as the probability that they have a dog, given they have a cat, times the probability of a cat. Just remember, you can flip these and say D intersects C, and it would be the same thing. So, 0.30 times 0.35. Which is 0.105. Sorry. Okay, so that was part C on number 10. For A? Okay, so probability of F given D is the probability of F intersect D divided by the probability of D. So F intersect D is 0.18 divided by probability of D, 0.32. So what's this probability? 0.5625. I'm sorry. And then for completeness, let's look at the probability of F or D, probability of F plus the probability of D minus their intersection.
I see someone right here.
You too.